Um, Hi, everyone. I would like to welcome you to the second session of the second day of the conference Women in Data Science in Alexandria. I would like to welcome the new participant to this pre-recorded talk, which is an introduction to machine learning. So this talk will overview some common tasks in machine learning as well as some more advanced types of machine learning. This is a pre-recorded talk that will feature Aurelie Jodelle Kemme, who is a Cameroonian data scientist who holds a Master of Science in Industrial Mathematics from the African Institute for Mathematical Sciences in Cameroon. She's currently an MS researcher at Quantum Leap Africa. The talk will also feature Colleen Farrelly, who is a senior data scientist at Datasembly, whose work has focused on natural language processing, topological data analysis, longitudinal data modeling, and time series applications, and measurement models across many different industries. I have to apologize because Colleen will not be here today, so she will not be able to take your questions or listen to your comments in person. Aurelie will be here, so if you would like to ask a question or make a comment, you can directly communicate with Aurelie, or you can contact Colleen via LinkedIn. Okay, I think we can start the talk now.
Hello, and welcome to an introduction to machine learning. Let's get started, shall we? I'm Colleen Farrelly. My co-presenter was not able to be here, but I'll be taking you through an introduction to machine learning. We'll be going through some common tools in machine learning today. First of all, what is machine learning? Machine learning is an AI field that hybridizes math and computer science. It's used to find patterns in data that can be used for a lot of different problems in industry. There are a lot of different fields of machine learning and types of applications. We'll be going through a few of the more common ones in this session and a few more in session 2. First, we have supervised learning. This involves making predictions, learning patterns, and finding what's going to happen next or on new examples. So say you're working with an emergency room to understand which patients survive heart attacks. You have data on a set of patients, perhaps patient vitals, demographics, maybe some intake factors, and an indicator of whether the patient survived or died. Your job is to find patterns that suggest survival or death in new patients who have those vitals, demographics, or intake. The most common model is the regression model. So in this case, we have an outcome, or Y, for a set of N patients. We have predictors. In this case, we only have one predictor, perhaps a vital sign. And we want to estimate the beta coefficients, or effect sizes, for this predictor. We also have random error. Whenever we're collecting data, it's not perfect. Machines can make errors. We can have parts of the model that are missing that we didn't think of collecting. So we also have this error term. We can have a lot more predictors than just one. The math works out similarly for this. We do a matrix inversion and we can calculate these values. However, in the real world, there are many assumptions of linear algebra that just don't work with real world data. So one example is genomics data. We might have 200 patients and 100,000 genes that we're looking at. This is a system that is not fully determined. And when we do the inversion, we have an underdetermined system. We might also have heterogeneity within our sample. So we might have subpopulations of patients. One example of this is addiction types with either a strong social component or a strong genetic component. Another huge problem that we run into is multicollinearity, where our predictors are correlated. So one main example of this is height and weight. Especially for young patients, height and weight are very highly correlated. And this is also going to pose problems when we try to invert our matrix and solve this linear system. However, machine learning has come up with a lot of great solutions to this problem that help us be able to estimate these beta coefficients and figure out the effect sizes and get a good model. So one of the approaches is to add penalty terms that make certain predictors fall out of the model entirely. This reduces the dimensionality and makes it easier to work with. We might also want to engineer features for input. For instance, BMI combines weight and height to get rid of that collinearity within a set of predictors. We might also take the approach of combining sets of models. If you've heard of random forest, this model takes sets of observations and predictors, builds a model, and continues doing this and aggregates across a set of models. We might also want to look at something that's nonlinear. So regression trees, classification trees, these allow us to have nonlinear predictor terms by having interactions as you go down the tree. It's also possible to use different optimization algorithms. There are a lot of these, and we'll go over a little bit about optimization later in this talk. It's important to measure model fit. So we need to account for variance. We might have really good prediction with our model, but there might be outstanding factors that we didn't consider that are going to improve understanding what's going on within the system that we're modeling. For instance, with our ER example, there might be factors related to the doctor who's treating the patient or the intake nurse who's on call when the patient comes in that influence what the outcome is. But if we don't measure it, the model can't add this in. So even if we have a model that predicts things pretty well, there might be other factors that are important for understanding the problem. In addition, we want to measure how well a model fits. So we want to look at the accuracy of the model. We might want to look at false positives or false negatives. There are some cases where you don't want to miss a true prediction. So with COVID, we don't want to miss patients who might need treatment or might be able to infect others. So false negatives would be really bad in that case. False positives can also be bad. Within the patient care context, you don't want to scare patients into thinking that they have something really serious. So the problem really dictates how we account for variance and how we measure how well the model is doing. Another key branch of machine learning is unsupervised learning. So imagine you're trying to figure out which sorts of customers are upgrading to your paid banking app. There's probably more than just one sort of customer upgrading. For instance, we might have a younger demographic and an older demographic who are upgrading for different reasons. What if you could use data to group upgrade customers by their app use patterns? This is exactly what unsupervised learning is aiming to do. One of the most common ways of doing this is with clustering. So we have a few common algorithms, k-means algorithm, dbScan. There's many other clustering models out there. But basically, we're using an algorithm to maximize the variance between groups and minimize the variance within groups. So we're trying to find these really tight clusters in space where everyone within the group is pretty similar on whatever variables we've collected. And hopefully there's not much overlap between these little balls within our space that we're considering. In addition to clustering, we also have rule mining. So finding good heuristics to parse out groups. There might be an age cutoff that we want to use. There might be a socioeconomic cutoff that we want to use within our customer base. It might even be geographical. Dimensionality reduction is another major part of machine learning and an active area of research. Imagine that we have really high dimensional data, maybe 10 dimensions or 100 dimensions, or even 1,000,000 or 1,000,000,000 dimensions. If we try to visualize this on our screen or in a presentation, it's going to be very hard to slice the data in ways that are meaningful. However, if we are able to wrangle this down to 3 dimensions, the problem becomes a lot more tractable to visualize in a way that humans can understand. In addition, dimensionality reduction can be used to create smaller sets of predictors to feed into clustering, regression, or classification algorithms with our unsupervised or supervised learning. One of the great things about a lot of dimensionality reduction algorithms is that they tend to uncorrelate the predictors that come out of the dimensionality reduction. So we can solve a couple of problems at the same time using dimensionality reduction. In addition, we're able to understand which factors, which predictors load on to these new dimensions. That might be useful in understanding what predictors can actually be combined to feed into a larger model. For instance, we might see that there's some interaction terms that we might want to consider before we do a regression model. Reinforcement learning is an exciting new field in machine learning, where algorithms continuously learn through penalties and rewards to achieve a behavior or pattern recognition that's desired in our application. This is closely related to intelligent agent learning, which reinforces good connections or inferences in chatbot deep learning processes. Another sort of branch of machine learning deals with optimization. This can be used in supervised learning, unsupervised learning, reinforcement learning, dimensionality reduction, and many other fields of machine learning. The basic idea is that we have a function that we want to optimize and a computational strategy to achieve that optimization. There are many examples out there. Some of the common ones are the least squares approach to regression, gradient descent. So gradients are used all over in deep learning models, in other supervised learning models. We also have evolutionary algorithms, such as genetic algorithms that find minimums and maximums of a function within this sometimes really complex space. Homotopy continuation has been explored in machine learning in a few applications, and this is an area that's ripe for development for any of you who are in geometry or topology. The expectation maximization algorithm comes up a lot in statistics, which basically looks at stepwise maximization of a function. Thank you so much. I hope you've enjoyed this presentation and know a little bit more about the options that you might want to consider within machine learning. And thank you so much for enjoying this presentation, and thank you to my co-presenter who wasn't able to be here. Hi, I'm Colleen Farrelly, and I am going to continue the presentation on an introduction to machine learning. Let's get started. So this time we're going to deal with some special cases in machine learning. The first of these involves time-dependent analyses. One of the tricky parts with these type of analyses are autocorrelations, which mean that what happened yesterday influences what happens today, and what happens on both of those days might influence what happens tomorrow. Without taking this into consideration in, say, a regression model, we can't get accurate predictions about what's going to happen next. A lot of these involve differential equation solvers, statistical models, and topological approaches. A differential equation approach might involve a special model to measure COVID patient volumes at local hospitals to be able to understand when the next wave might be coming that might overwhelm local resources. There are also statistical approaches to this, such as latent transition analysis to understand educational attainment groups over time that might be separated out by region, by language, by socioeconomic status, or by other factors. There's also a way to deal with time series and these time dependencies using topology. For instance, it's pretty common these days to look for transition points in stock markets, such as the South African top 40 stock index, using something called persistent homology, which basically looks for change points within the time series where the behavior is switching. So you might see spikes and crashes when you're looking for those transition points. Spatial analytics also involves autocorrelations, except these are across space rather than time. For example, there might be two food markets in Cairo, and the prices changing in one market might influence the prices in a second market. Or in the case of buying from a much different region, the prices of imported goods in Cape Town and the prices of imported goods in Alexandria may be linked to a supply chain that's supplying both areas. We can also have time series components to spatial analytics. For instance, weather patterns and disease spread are both influenced by time and by space. Network analytics is another huge branch of analytics. And a lot of these algorithms are rooted in geometry, topology, and differential equations. So those of you who are really interested in more of the geometry topology side may be interested in this branch. For instance, we may want to understand social media influencers by looking at the topology of the network and which vertices or social media personalities, influencers are most central to the network. You may also want to look at spreading processes on networks, such as the spread of public health disinformation across a community through the social network within that community. We can also use a tool from geometry to identify network backbones and important links within the network. This could be important within an electrical grid to identify important transformers and connections in the city where we might want to beef up the support for those key pieces to be resistant against natural disasters or accidents that happen around them. Natural language processing is another huge part of machine learning. There are many examples out there. Let's visit a few of them. We could use sentiment analysis to track customer satisfaction with a product based on customer feedback that is given through a form or an online application. We might also want to look at the text or keywords within an email to understand whether or not the email might be spam or not spam when we're filtering out spam emails. It's also a branch of AI that's pretty common in healthcare these days. There are a lot of models that look at text input and communication between patients and doctors to understand how things are described and how different conversations lead to different health outcomes. There's also a big need for translation. So for instance, there might be material that's in Arabic, French, English, or Swahili that needs to be translated to a native language or translated back to those languages. Natural language processing, GPT-3 in particular, has gotten pretty good at being able to do this translation. In addition, a lot of applications like Alexa use text-to-speech signals to process applications so that when a user is interacting with a program, they're able to actually have what they say translated to text, processed, translated back to speech in your application to speak out the response to you. There are many, many more examples, and this is a rapidly growing field of AI. Computer vision is another hot topic in machine learning. Images are usually analyzed by one of two approaches, either the convolutional neural network, which is a type of deep learning, or through a topology and geometry-based algorithm. Topology and geometry were the main ways of doing this before neural networks were developed for this purpose. A lot of tasks come from looking at images, including classifying objects such as endangered animals that are captured by trap cams, predicting consumer response to an ad campaign's image, facial recognition, which is really fraught with biases these days. If you're building one of these applications, you probably want to use faces that have been collected locally rather than some of these repositories, as they're known to be fairly biased. Processing images is another huge task of computer vision, particularly within the medical field. So these algorithms can be used to turn image data into data that's a little bit more compatible with traditional relational database data. In addition, all of these things that can be done with images can also be done with videos. And social media has given us an abundance of videos to analyze these days, including TikTok, YouTube, and others. Outlier detection is another key part of machine learning. If there's bad data going in, the model is going to learn on non-ideal data and have worse prediction than if we had clean data going in. So outlier detection is often used as a pre-processing step with data. However, there are some instances where outlier detection itself is the problem at hand. This is one of the more common things within fraud analysis and intrusion detection, and also within change point analysis. So returning back to our spatial and temporal data sets, we may want to look for outliers where the behavior of the process that we're measuring is changing. Motion planning is a key part for autonomous systems. And these applications tend to be rooted in homotopy and other areas of topology that deal with path planning. It's an interesting field, but fairly specialized within robotics. Fuzzy logic is another fairly robotic part of machine learning, and it can be really helpful when dealing with the uncertainty of decisions. So basically, these methods leverage probability theory and overlapping sets to classify decisions into more than one bucket at the same time. And it's a big part of robotics and intelligent agent systems where uncertainty is just a part of the application. The next frontier of machine learning seems to be quantum machine learning, where machine learning algorithms are translated to quantum computers. These typically involve network algorithms, supervised learning, and some physics-related algorithms. It's likely that we'll see more of these in the future, but these tend to be some of the more math-heavy fields of machine learning. Thank you so much, and I hope you've enjoyed this and have some direction on where to dig in next to start your journey in machine learning.
Anyone would like to ask a question or anything, You can do this in the chat, or you can do it now directly. If you would like to ask Colleen a question, you can contact her via LinkedIn. Well, I would like to thank everyone here today for coming, and I would like to remind you this is not the last day of the conference. This conference resumes on Monday. There are 2 sessions on Monday. There is a morning session with Diletta Martinelli, which is an introduction to linear algebra and matrix computation. And there's another session in the afternoon, also led by Diletta Martinelli, which is an exercises session. I hope all of you will come back on Monday. I would like to thank Ihsan Shams, who is the organizer of this conference. Everyone.